Okay, welcome back to the next part of this model fitting and experimental modeling. Okay, okay. Now, as mentioned in part one, in part two, we are going to look at the methods. So in this case, we just focus on three methods. Okay, basically, if you notice from the previous part one, the model fitting is normally focusing on the deviation. Okay, deviation from the real observe, okay, from the observed data set, for example, versus the real data set, something like that. Okay, so by the end of the day, all right, by the end of the day, how can we do just that? Okay, so you look at this one, we have the Chebyshev Chef approximation criterion. The second one, minimizing sum of absolute deviation, and the third one is least square criterion. So what are these three different criterion talks about? Okay, so we start with the Shelby Chef first. Okay, the idea of Shelby Chef approximation criterion is just focus on the absolute deviation. Okay, absolute deviation meaning that if you can recall back on part one, where you have point A, B, C, D. I cannot remember which page, but when you have point A, B, C, D, and then if you notice point D goes so far away from the uh, uh, approximated line that you have. Okay, so meaning that you focus on that particular point only, right? One by one, you find the largest valuation, and then you minimize all this, minimize the largest value, absolute absolute deviation that you have. Okay, before it, if you notice absolute, what does it mean by absolute? Okay, meaning that it doesn't matter if your point is up of your line or down the line. Okay, it does not talking about the location part of it. Okay, it talks about the distance, okay, between those point and the projected line. Okay, so that's why you are talking about absolute, in case you wonder why we talk about absolute so much, what's the difference, right? Okay, so that's the meaning of absolute deviation. We just focus on the distance only. We don't care about the sign, whether it is upper or lower, negative or positive, we don't care. We just focus on the distance. Okay, that's why we want to find the minimum of the largest absolute deviation. Okay, all this model, all these three criterion, okay, all these three criterion just focus on this. If you notice, all are similar. Okay, yi minus fxy. This one is the one that I mentioned. If you have this one and this one, okay, so you can imagine this is your yi, for example, this is your fxi, for example. So this is your one, yi at I particular time, this is your fxi at fxi particular time. So these are the distance that the distance that we want to focus on. In this case, we call that a deviation. Okay, so how to do just that? Okay, so it's a little bit like overwhelmed. It's a little bit overwhelmed for you, isn't it? If you suddenly say, okay, I need to know maximum y I minus FSI. Okay, so I give you a simpler version first. Okay, but this one is just for you to revisit and make sense. How does this distance means? Okay, so it means like this. For example, if let's say you have this issue, okay, you have three line, you have 3 points that represented with a straight line. Simple, isn't it? Okay, so your measurement, your early measurement, your A to B, you have 13 centimeter, whatever. Okay, and your B to C, you have 7, and then your A to C, you have 19. Okay, that is a measurement, right? That is your measurement. But in reality, your AC, the point from your A to C, is actually 20. So where this one where is one? Okay, you are losing one measurement. Okay, 1 cm measurement there. Okay, your measurement estimation is 19, whereas your AC, the normal valuation actually is 20. So this is the example of fitting the model. Okay, but in a simpler version. Okay, so how can we address this 1 centimeter issue? Hmm. Okay, it's a little bit tricky. If you want to address this 1 centimeter issue, for example, this is how you're going to use this approximation criterion. Okay, what you need to do, okay, you need to assign values, okay, to three line segment. Okay, the idea is that, um, how to say that? Okay, give me some time to think through. Okay, this one value you should distribute equally. You should distribute equally to all the line that you have, meaning that you distribute one to your AB, BC, AC, because we are dealing with these three different issues, right? Okay, do not forget AC as well. Okay, so you distribute this equally. When you distribute this equally, okay, meaning that earlier your AB equal to 13. So when you distribute equally, remember distribute equally meaning one. Okay, one, one. It will become distribute equally. Okay, one it will become equally three. Okay, it will become one third, one third, one third, right? So that what? Oh, sorry. So that it means by distribute equally. Okay. So in this case, you now since it distribute equally, in this case, you now your AB now become okay. If you get confused, okay, revisit this again. Oh, now now I'm losing my pointer. Okay, so your AB now becomes 12 to 3. Okay, because remember, I don't care about the plus or minus sign. I just care about the distance. Okay, distance meaning that one distance is either you want to reduce or you want to increase. Doesn't matter as long as you are dealing with one third of these particular issues, and it has to distributed equally among AB, BC, and AC. So if let's say one third, it does not make sense if I put 13, uh, getting it bigger into 13 one third, isn't it? Because you are already lose out 1 centimeter. So how about that? Right? Okay, so that's why you reduce 12 to third, and then your BC you also reduce, and it becomes 6 to third because you take out one third from your 7. Okay, so 6 to 30. But what about AC? Will your AC become 17, 18 to 30? Okay, but before you say, yes, it is. Okay, but you have to remember, whatever happens, your AC must be equal to your AB plus BC. Okay, that's why your AC now becomes Eh, okay. Your AC now becomes 19 one third. Okay. You still have one third, but if you notice, it's not the same as your AB and your BC, isn't it? Because right now, instead of decrease, now it becomes increase. Okay. But as I mentioned earlier, your one third is not plus or minus. It does not mean that you plus everything with one third. It means that you distribute one third equally. Okay, you distribute one equally, meaning that you are talking about a distance, not the valuation, the additional valuation inside your model. Okay, you are talking about distance. Okay, that's why if you notice, you have 19 one third for your AC, and it fit with the idea of this requirement. Your AB plus your BC must equal to your AC. In this case, 12 to third plus 6 to third, you will have 19 one third. Okay, do you get it? I hope you get it. Okay, so please digest this a little bit before you proceed with page 17. Okay. It's okay if you want to pause a little bit. Okay, so for those of you who already digest this information, now we proceed to page 17. Okay, so what's the big deal about that issue? Okay, now we try to translate that issue into the real deal. Okay, how can we able to construct the valuation for our uh, uh, the exact weight, the exact weight, the one earlier that we said, oh, we just assume this one third, and then we're going to see actually what is our value, yeah, okay, what is our um the real true value for my BC. All right. And what is the true value for my AC and so on? Okay. AB and BC, because we know our real value for our AC is 20, right? That is the true value. Okay. So, how to move about? Okay. So, let's say you introduce X1. Okay. So, X1 represent the true value of the length of the segment AB. That is a true value. You don't know that true value, right? But you don't know your measurement value. Your measurement value is 13. Okay. So if let's say your true value minus your 13, your measurement value, assuming that this true value minus your measurement value, you will get the discrepancy value, okay? The error value, okay? The value that you feel like, so where is this one lose out? Okay, so you introduce R1, okay, for your discrepancy value for line segment AB, and then R2 will represent the discrepancy value for your line segment BC. R3 represent the discrepancy value for your line segment AB. Okay, so instead of talking about difficult words like discrepancy values, okay, so we actually highlight our this R, we call that a residual. Okay, so if you ever heard about residual effect, residual values, okay, so this is what it means by that. Okay, the different value between your true versus your measurement value. Okay, so that's what we call a residual value. Okay, so let's say your R1, R2, R3 is your residual right now. So this makes sense, right? Okay, this makes sense, right? We have x1 minus 13, you have r1, x2 minus 7, r2, and then this is um, this ab plus BC. It should be something like 20, right? The not the real value, the true value that we know already. Minus 19. 19 is your observed or measurement value for your AC. You will get R3. Okay. So if you notice, I put it over here so that we need to revisit this once when we do the solution later. Okay. So digest this one as well. Okay. Once we have this under our command, and then we start to proceed, what is our main intention for doing this Shelby Chef approximation criterion? Okay, so earlier we noticed that whatever that we do, we want to minimize the largest absolute value here. So we know our largest absolute value is R. In that case, your residual value. We want to minimize this. Okay, so this minimization of this R must be subject to these three conditions. Okay, the subject of these three conditions meaning that what? Okay, my R1 must be less than R, my R2 must be less than R, and my 3 must be less than R. Okay, so what is R? R, always remember R is your largest number. Okay, largest residual number. You don't know what is your R, but you know you want to you want to find the largest value for you want to find the largest value first, and you want to minimize this largest value. Okay. Hmm. Okay, so this is your condition. Okay, this is actually your condition. But this is what it all make a little bit of a nuisance. Okay, we are dealing with absolute value. Okay, and you know absolute value. The idea behind using absolute value to is to create your distance. Okay, to create the concept of distance, not on the concept of, as I mentioned, plus or minus. Mm. But the minus side of the value, absolute value, you cannot just simply solve your value as it is, because you know, um, in a nutshell, once you have a absolute value, once you need to solve this absolute value, okay, it is not equation based. Okay, it is not based on equation, it is absolute equation. Okay, inequality. Okay, so in this case, see, from here you need to transform your absolute value and your inequality into this relation. Okay, that is why it is not that easy. Everyone cannot just simply solve Chebyshev approximation not using any mathematical tools. Okay, you cannot do that because it's going to get involved with this inequality. Okay, so that's it. That is the problem. Okay, so again, as I said, if you are a good mathematician, you can always find ways to solve your problems. Okay, so if let's say this is your problem, okay, it's okay, no problem. Okay, from here you can always transform this into two things, right? The first one is consider this one, and the second one is consider this one. Now you get a more solvable inequality, isn't it? Okay, so that is what our intention. Okay, so how to do just that? Okay, so remember, this is our relation. Okay, we have this relation. Okay, so right now I'm going to utilize my relation, okay, from the previous page. Okay, I'm going to utilize that and to transform my page 18 into page 19. Okay, so looks complicated, isn't it? Okay, so actually these two, eh, okay, these two coming from the first one constraint on the previous page. These two coming from the second constraint, and these two coming from the third constraint. And then if you notice, there is no R1 anymore. Okay, there is no R1 anymore, right? Why there is so? And suddenly you have X1, X1, X2, X2, X1, X2, X1, X2. Okay, why there is so? You go back here and you see that, oh, these are the relation that I have. Okay, these are the relation that I have. Okay, so I think you need to pause a little bit and then reconstruct this relation. Put the relation from page 18. Try to rearrange your inequality into two parts, and then for example, your first okay, I give you one example. Okay, give me some time so where to move about. Okay, if let's say this is my first constraint earlier, right? Okay, my first constraint, meaning that like this. Okay, all right, so this correct, isn't it? Okay, wait. double check. Yes, okay. So that is my constraint, my first constraint. Okay, so once you have this, blah blah blah, you do it. Suddenly you know that this is actually you can reduce this into this is your first constraint, and then another one because you are dealing with absolute value, isn't it? Okay, so absolute value. That's why you have negative here and positive here. Mm, okay, like this. All right, and then from here, okay, I give it a little bit like this. All right, okay, from here you can see this is your R1. Okay, and this is your R1. Okay, so you can just simply substitute your R1 here with this. Okay, why we do all this messy thing? Because we are a mathematician. We like doing this. Okay, hope you don't get annoyed with that. But the idea is that because you want to minimize R, okay, you don't want to minimize R1. Okay, that's why once you need to minimize R, you need to make sure that all your subject to must also equal to R, isn't it? Because if not, how can you quantify your R with different R at the bottom? That's not make sense, right? Okay, so that's the intention. Okay, that's why. So you do the same thing for your this one and also for your this one. So by the end of the day, this is what you get. Instead of having three conditions for your subject to on page 18, now you have six. Okay, that's it. Okay, and then if any one of you want to ask, okay, then what? Okay, is it just as it is? Okay, no. Okay, actually earlier we cannot normally do a soft Shelby Chef approximation criterion because this is the example of why I say it is complicated to solve. But now, on the previous example in your probabilistic modeling, no, on the earlier, okay, deterministic modeling where you have linear programming, remember? Linear programming, you need to maximize or minimize certain subject problems, right? And then objective function, and then you have lots and extensive different kind of constraint. You can always simplify this, put this under you can solve by using simplex method, doesn't matter. You can put inside the QM4 windows, doesn't matter. And you click, then you get the valuation. You can get your R, X1 and X2 automatically. Okay, try it if you want. Okay, and if you do that, all right, if you do that, by the end of the day, actually you will have R equal to 1/3, X1 equal to 12 to third, and your X2 equal to 6 to third. So it's jive, all right? It's jive with the assumptions that we have earlier. Okay, so this is one. Okay, we only cater one first, and then next we are moving forward to the next criterion, and the third one we are moving towards the last criterion. The last criterion is the most common. Okay, ready? So, the second criterion. Okay, this. Okay, the second criterion. This one, minimizing the sum of the absolute deviation. Okay. Okay, what about this? Okay, we minimizing the sum of the absolute deviation. Okay, this one is actually, okay, how to call this? Okay, the concept is interesting. Okay, why? Because we are talking about the sum, okay, of the deviation. Okay, we don't talk on a individual absolute deviation, meaning that we don't necessarily identify the largest and then we extract the largest and find the minimum, okay, from this largest value. Okay, we don't do that, meaning that we are more flexible. We try to merge a little bit our line, okay, to meet as many point as we can in a more cordial manner, meaning that, oh, actually the points is quite nicely put together. Doesn't matter it fits exactly in the line, but the sum of this deviation is minimized. It makes more sense, isn't it? Okay, it makes more sense. Okay, the concept is still the same. You have to find the residual actually. Okay, your valuation true versus measurement. Okay, but the idea. Okay, the problem here. The problem here. The problem here. If let's say you have this. Okay, uh, then we need to minimize. Okay, by right, you know, okay, once you have all the valuation inside here, you calculate blah, 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 blah. It is a summation, right? It is a summation. So if you need to find the minimum point from this valuation, by right, you need to find the critical value, isn't it? Because you are dealing with a model. It is also just a simple model, typical model. So it doesn't matter whether you're, if linear line, then you are lucky. If let's say you are talking about different line, whatever it is, your model should be, you should make some derivation, right, from the model, because by the end of the day, you need to find the critical point. Critical point is just the tangent line equal to zero, isn't it? Okay. Hmm. The problem with this method is that, okay, uh, how can you find the tangent line, or how can you find the maximum value, oh sorry, the minimum value, in this case the critical point? How can you find the critical point when you have a function that is not continuous? That's the main issue. Okay, because if your function is not continuous, can you find the critical point? Can you derive the point according to the valuation on your certain points that you want to consider? You cannot, right? You cannot. Okay, if you forgot about that, okay, you go back to the calculus lesson. Okay, you cannot do that. That is the main problem with this model. Okay, because we are okay, in case you feel like, what's the significance between those two? Okay, the significance is that we are dealing with an absolute value. Okay, absolute value. Absolute value does not give you a continuous function. Okay, so if you don't have the continuous function, you cannot make the derivation. If you cannot make the derivation, you cannot find the critical point. That's the main problem with this issue. Okay, that's why we don't talk much about this. But the concept is nice, isn't it? The concept is nice because you want to find the sum of the absolute deviation, and then you're going to minimize this sum so that the line should be very, the line should nicely cater for all the points that you have, but then realistically you cannot solve it. Not much, not much you can, not much you can do about this. Okay, that's why we don't talk much about this minimizing the sum of the absolute deviation. Okay, moving on. The third criterion. Still with me? Okay. The third criterion. Now we are talking about this criteria. This one is the most common. Okay, why that is so? Okay, let me tell you this. Okay, we call this a least square criterion. Our goal is still the same. We need to find the parameters of the function to minimize the sum of the absolute value. Okay, but then now we are talking about square. Okay, we are talking about square. Okay, that's why we call least square criterion. Okay, we are talking about the absolute value of a square. Okay, why that is so nice? Okay, because first you still get the benefit, okay, from the previous criterion, meaning that the one that we cannot solve earlier. You have the sum, okay, the sum of your absolute value, but then now you are able to solve this value because we don't deal with absolute value anymore. Okay, that's why we introduce square. When we introduce square, your absolute value suddenly diminish. in a way, isn't it? Because if let's say we open the valuation of your absolute value, we get even negative value, isn't it? We get even the negative value, but then by negative value, when you square your negative value, you still get the positive value. Okay, so you can work out the solution for this criterion. It's like that. Okay, so we are going to proceed with the ways of solving least square criterion in part three actually, because it needs our attention more, and it's more interesting to look at. Okay, it's just that from now on, I'm going to show a little bit the concept behind getting the geometric interpretation of this particular problem. Okay, so this one I'm going to get my hand dirty a little bit. So if let's say, okay, you are dealing with, just I hope you follow me over here. Let's say you are dealing with you are dealing with three data points. All right. So let's say you are dealing with three data point, and then let's assume this one. Okay. Just assume this one first. Okay. And then you can see over here, if let's say my three data point, my data point representing this. Okay, so that's my three data point. Okay, okay, so okay, okay, this one is for you to understand a little bit. Okay, so how can we represent, okay, the valuation in a geometric sense? All right, the observed and the predicted values. Okay, so in this case, you try to create your understanding on your geometric interpretation. Okay, it's like this. Okay, let's say since we are dealing with three different so it will be make sense if we transform this 1 to 3 into three different axes, right? So let's assume that now my R1 becoming three axes in the vector field. Okay, so if let's alamak, sorry, okay, so assuming I have X, Y, and Z. Okay, so assuming my first vector, okay, my first item is R1, uh, R2, and R3. All right. So assuming if let's say this is my vector, okay, this is my vector, R1I, R2J, R3K, assuming it's a vector, right? Okay, this is just for the geometrical interpretation so that you understand a little bit more, okay? So assuming, remember back your vector function, okay? So assuming this is your R2 and this is your R3. Okay, if you need to uh, transform this, okay? Okay, okay. Magnitude. Okay. 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 If let's say you have a vector, how you're going to transform it into a magnitude valuation? Okay. So if let's say I have the magnitude, I want to find the magnitude of my R. Okay. By right, you can get it by doing this, right? This is straightforward, isn't it? This one is your vector. Okay. Put all your vector inside your item inside that, square them both together, and you find the square root of it, and then you get the magnitude value for your R, right? So the idea here is if you want to minimize, okay, if you want to minimize R, okay, if you want to minimize R, by right, you can minimize R2, right? Makes sense, isn't it? Okay, it makes sense, right? Okay, so by using this idea, okay, because it is just a magnitude, okay, by using this idea, so you utilize this concept of maximizing R2. Okay, this will only become you trying to find the summation for your Ri. Okay, this is just R1, R2, RT, but you square them together, and then your Ri is just a comprise of your observe versus predicted values, isn't it? Okay, because you already assume that previously. Okay, the rest just follow together. And then if you are having this, oh sorry, and then if you are having this, okay, now you can find your critical point as usual. You can minimize this. Okay, so um, like that. Hmm. Makes sense, isn't it? Okay. So basically, that is why, okay, we are able to find the minimization of your valuation for your observed versus predicted values in your least square criterion. Okay. This is just the basic of it. We are going to look at this least square criterion because this one is most commonly used in the part 3. Okay. So you need to think through a little bit, and I really recommend you to read book by this Giordano Fox and Horton for you to get the hang of it, and for you to try test your understanding on the problems that they have in the book. Okay, so this criteria I just recap and summarize a little bit. If you have Chevy Chef criterion, what you need to do is you minimize the largest absolute deviation. Okay, the difference between them is just that Chebyshev criterion does not include with the sum of the absolute deviation. It's involved with a single point. All right, single point give more weight to single point potentially having a large deviation. Remember back your D situation. All right, and then the second criterion, now they treat each other point equally and average this deviation, but unfortunately, um, it has a problem of non-continuity. Okay, and then the third one, you have a least square. Okay, the least square, you get the same information, the same basic idea as your second criterion, and now you are able to solve it. Okay, because you don't deal with absolute value anymore. Okay, so this is a little bit quite extensive, I noticed, but I think you can carefully revisit these uh, two parts actually. Okay, these two part and get the importance gist of it. Okay, before we proceed to part 3. Part 3, we are going to look at how can we choose model. Can we use the least square criterion to solve it, and what are they? Okay, and then late on the later part, we are starting to look at the a little bit on, but a little bit only. All right, on polynomial. Okay, how to adopt the polynomial interpolation. Okay. Okay, quite interesting. All right. Okay. So I hope you enjoy the video and get benefit from it. All the best again with your acquiring knowledge in the future, and do not stop learning. Okay. So I'll see you guys in the next lesson.